Hello, Paulo, Philippe, Professor Kuo-Fong Ma.
Yes.
You're here.
How was the team?
Hello, that. How are you doing?
I'm good. How are you?
Good. Did the Sim 3 discussion went well?
I think it went well. Yeah. How about your team?
Yeah, it was interesting.
Interesting.
Mixture of different approaches. It was
Yeah.
we would like to talk more actually, but we are not.
Yeah, right. Right. Yeah. Yeah.
But it was a good discussion.
A lot of discussions. Yeah.
It was a good discussion. So very good.
So I'm not sure when we have to start exactly. Where is the time?
Okay.
Maybe we need to wait a little bit more participants because we are now just 10 attendees and 7
sure.
panelists. So maybe I suggest to wait a little bit more, just in order to reach a critical number, and then we can start. Yeah, sure. Bruce correctly suggested us to wait 2 minutes because people are already still in the poster viewing. So let's wait, and then Philippe, you can manage. Okay, so I think we can start. So please, Philippe, now it's your turn to present the keynote speaker.
Thank you, Paolo. Dear all, I'm very pleased to introduce Kuo-Fong Ma, Professor Kuo-Fong Ma, as the keynote speaker for both Theme 3 natural hazard and megacities and Theme 4 monitoring methods. I am Philippe Jousset at GFZ Potsdam, and I'm also president of the seismology division at EGU until 2023. And so, as I said, it's my great pleasure to introduce Kuo-Fong Ma. She was asked to give a keynote for both themes of this conference. As we'll see, her background and her knowledge is covering basically both lines of these themes. And Kuo-Fong Ma is currently the chief scientist of the Taiwan Earthquake Center at the Institute of Earth Sciences in Academy Sinica. She is a distinguished research fellow at the same university, and she's also director of the Earthquake Disaster and Risk Management eDream Center at the National Central University as well. She obtained a PhD some years ago in at the Caltech, California Institute of Technology in the US, and she is very well awarded as well. She received the Oxford Medal in AOGS this year. She is also an American Geophysical Union Fellow, and she received also in 2013 the National Professorship in Mathematics and Natural Science from the Ministry of Education. So, Kuo-Fong Ma, I'm very pleased to give you the word for an excellent talk, I'm sure.
Thank you so much, Philip. Let me share my slide first. Can you see my slide? Can you see my slide?
Yes, we can, and it's full screen, so this is perfect.
Okay, thank you. Thanks, Philip, and thank you everyone for this invitation. I hope I can really cover these two subjects you cover in the theme 3 and theme 4. I enjoyed the discussion for this the topics on the in situ monitoring, and also the important to monitor the natural hazard for the megacity. So I put my title of this presentation as the evaluation and the monitoring the seismic hazard potential of megacities for resilient society, application from forefront of earthquake sciences. I'm Kuo-Fong Ma again from the Institute of Earth Sciences, Academia Sinica, and also Department of Earth Sciences, National Central University, Taiwan. Well, it's also good that indeed I have two important projects to carry on this couple of years, cover these two topics. So I'm really happy to share our project with you and maybe hear your comments for our future projects as well. So let's come back to the very big questions we always ask as a seismologist. We always wonder how earthquake was initiated and terminated. And to me, I feel if we can possibly understand these two questions, then we might have the hope for earthquake prediction or to have a better forecasting for earthquake hazard. But we are still on the way of doing that to understand more of those topics. Before going to that challenging topics, we might also want to ask, how can we understand or what kind of mechanism to cause the damages? And to this, then we might be able to mitigate the hazard. That's actually very important to general public rather than the scientific questions, but how we can learn from science to really help the people or the government to make the policy to reduce the impact from the natural hazard. And then to that, then we become focused on whether we can predict the ground motion in amplitude and period to reduce the impact. And because from that, and with maybe also the buildings or any key facility, then we are able to have a better structure to avoid the impact for this from the earthquake, what I'm saying. And for that, I feel it's very important to have a better mapping of the seismogenic structure. Because from that, then we are able to have some idea of this, the source or fault model. Then we can apply our knowledge for the wave propagation and also the calculation to capture the possible phenomena at site. And that's actually the focus I've been carrying on for a couple of decades. And I hope I can come to the subjects and also to using the future science to advance all these questions. So come back to the issue of the mega cities. These are the map for the Taiwan is pretty small, but very complicated in tectonic structure. And this is the location of some mega cities in Taiwan and also bathymetry around Taiwan. By bathymetry, you can see there's a complicated bathymetry offshore Taiwan because we have two subduction zones to the north, which is Ryukyu subduction zone, which actually give the high impact to Taipei and Taichung. But in the same time, we also have another minor change, which actually has potential for the large tsunami, which might impact our southwestern Taiwan. So Taiwan is actually in the location of all this threat for the large earthquakes, and not to mention other natural hazard, but I focus more on earthquakes today. So because of that, and for all these topics, then in 2013, we began to form a Taiwan earthquake model, which I think is very important that we can have a good platform to put the science on the forum that people can discuss and also apply to engineer. So engineer know what we are saying, and then the results can deliver to the government and really give the impact for the social sciences. So in Taiwan, sorry for some Chinese here, but basically you can see we are have many active faults inland of Taiwan and the northern Taiwan and central Taiwan and southern Taiwan. And in northern Taiwan, specifically, I would like to focus today is the Taipei metropolitan city, which we actually have one active fault, Sanjiao Fault, across the boundary of the Taipei Basin. But not just for this active fault. We actually experienced many damage in Taipei from very far distance earthquakes. For example, the Ryukyu subduction zones, which potentially have a magnitude A+ events from the subduction zone. This subduction zone will bring some impact to Taipei, especially for the long period ground motion. So in this decades, actually for all this effort, fortunately our government understand the impact from very large earthquakes. So we have the attention from multiple agencies. For example, our Ministry of Science and Technology as a funding agency, they give us a project to carry on important subjects for this topic. And we have the involvement for the NCDR, which is the agency for the disaster reduction, which can really deliver the hazard into the risk. Then we have the involvement from the Ministry of Interior that manager of this for the fire department for the rescue and also the building code. So we are in a good track, but we try to still hurry up for our future big ones to get prepared for that. So is that my echo? Is that echo pretty loud? Okay. Okay. Well, then, so actually for the exercise we had now is from earthquake source model, and then to go to the loss assessment and then to the policy. But before that, we need to have a good monitoring that we are able to map better seismogenic structure to understand what's the potential source for the future large earthquakes. So to focus on the Taipei metropolitan, as I mentioned, although we have one Sanjiao Fault, which is actually relatively less active compared to other active faults. But in Taipei, we experienced several impacts from recent large earthquakes. For example, one which maybe some of you know is 1999 EGU earthquake. Actually, it was today. It's 1999 September 21st. So today is the 22nd anniversary of this damaging earthquakes. So this earthquake actually in the central Taiwan, but a couple of buildings collapsed in Taipei because of the basin effect. That's actually very important issue to tackle. And the other one is 1986 Hualien earthquake. Again, it's offshore here, and this one also give the impact to Taipei. And those are the earthquakes at least in in the lifetime, most of us are now, but before that, whatever we have experienced, in 1920, we have this nuclear subduction zone making an earthquake about 100 years ago. And we don't know what we will have become if any earthquake like this, again, to Taipei, which we have now all these high-rise buildings. And that's something we want to exercise to understand how much impact we might experience for the earthquake of that kind. And the other one is 1909, right beneath Taipei. That's a subduction zone events, the depth of 80 kilometers. And then the other one is 1867, which may be the only one we know so far, really from the Sanjiao Fault offshore northern Taiwan. That one is also the only one we have in record for the tsunami. So this is actually all the study we try to learn more, especially for the subduction zone here, that comes to the subjects. Another subject I will carry on now for the later on for the MIDAS project, why it's important to have a good monitoring at this corner right here to understand the possible interaction of subduction zones to inland Taiwan. So again, come to the hazard potential. We published this seismic hazard map in 2015, November. And at that time, we focus on, we have a high impact southwestern Taiwan, and this is very high, very short recurrence interval of this Milun fault. And unfortunately, or fortunately, that we actually capture all this in 2015, because in 2016, we have one Milun earthquake in southwestern Taiwan, actually give the impact to the Tainan city to have one collapse of high-rise building, which was built in 1980s, that actually give our government very important hint that we have to focus more for this building made in before 1980s, which we have less knowledge in earthquake science and engineering. And then in 2018, another one in Hualien, this Hualien region, the rupture from offshore go all the way to inland, even though it's only small part of inland for the Milun fault, that also again to bring some damage. Although the damage is not so severe like the EGU earthquake, but nowadays any one or two buildings collapse or any fatality is always an important issue to understand what's the reason and to save all the lives if we can. So the whole this is because of this Milun subduction, Milun fault is right linked to a subduction zone, as I mentioned earlier, for the nuclear subduction. And that's how I will address more of our MIDAS project in the later of my presentation, why we want to bring this, the new idea for the fiber, optical fiber to this, the vertical boreholes, and also inside the GPS and so on, for actually all the subjects we discussed just earlier this afternoon is a good subjects that we actually will cover in this project. But before that, I still focus on the impact for the mega cities. That in 2015, we published the first national hazard map. We are a little bit late to publish the seismic hazard map because people are always cautious about because the highly population, they are always cautious about where the fault is and how can our government take all these challenges when the buildings are next to the fault. But fortunately, that the open data policy and also the new knowledge to everyone, now this kind of national hazard map become acceptable to the government and also the general public. So in 2020, we have another version which considered a multiple fault rupture that for the small segments, they might rupture at once. For example, this 1935 Taichung earthquake rupture two or three segments. Well, so then we published this for the hazard potential for the lifetime of people might experience in Taiwan. And you will see that almost everyone in Taiwan in their lifetime will experience a magnitude for the intensity of 5+, which is actually up to about 250 Gauss in a way. So that's at least that the building code or people have to get prepared for this kind of shaking. And for the buildings or important facilities, we have this returns period of 500 years. And you can see, especially in southwestern Taiwan, the intensity 7 is expected, and also in this Longueuil Valley, which also high impact for intensity 7 and other region. So no matter what, we have to get prepared for the strong shaking in our lifetime or for our structure as well. Well, I show you one of the example for the event in 1986. I have to say I didn't pay attention to this earthquake because at that time I was a student. I didn't really pay that much attention. And also that's really just before the time that all this digital data become available. However, I found this earthquake was a really important earthquake to study, even though at that time the station's only trigger mode. However, Taiwan already had some building array at that time. I was actually amazed by how much instrumentation we had put on in 1980s. This is earthquake, as I mentioned, in 1986 in Hualien, but the impact to Taipei, these pink cross are the damages from the earthquakes. And the triangles are the stations at that time from building array. And you can see for the ground floor, this is ground acceleration, maybe to 100 Gauss, which is still pretty high, like 5 minus intensity at this now intensity scale. But if you go to the buildings for 10th floor or 8th floor, for example, you become like 400 Gauss. So the amplification of the shaking to the high-rise building is a very important issue. And that's why we also now try to put into some building array to understand the shaking from the ground to the buildings. And these are some photos in 1986, which actually bring the impact to Taipei to a market that building collapse. And these earthquakes actually is important earthquake for Taiwan is because that's how we become to have this Taiwan Strong Motion Implementation Program, TSMIP. And that actually captured the earthquake of 1999 GG earthquake. Then we can contribute our data to the whole world for the to understand how the waveform look like for the large earthquake and in the near field. And in the same time, because the Hualien earthquake have offshore Taiwan, Taipei, to some distance to Taipei, and that's also the idea for the earthquake early warning, which is now widely adopted in Taiwan and also many other countries as well. So because of the topic of our theme in theme 4 is seismic monitoring, in situ or remote monitoring, I have to say all my career, actually I thanks to all this high quality data we implemented since 1991. Because of the 1986 earthquake in Hualien, as I mentioned, then we have all these three components, digital data, island-wise, about 900 stations, and it's all open to everyone to study, and that's how I can really to understand the earthquake more, to the earthquake engineering and so on. And not to mention just the strong motion, but also the GPS and stratometers, and actually more for the borehole stations and others like the low cost sensor for the P alert for early warning. And I will show you how good the performance of all those low cost sensor, which actually we addressed in Indonesia. I actually give a comment is, well, the rotational seismology is good and important too, maybe in a way, but it's expensive. But this low-cost sensor is good to capture important feature for the understanding of the earthquake characteristics. Well, so that was in 1991. So like 30 years after, for now, in 2021, we actually proposed a Belmont Forum project called Resist. As I mentioned, we try to implement the sensors not just at the ground, but also to the buildings. So we work with engineers, and also we work with the social scientists, how people digest the data, what do they want to know, and what can we deliver? Whatever we deliver is important to them or not. So to this project, we also take advantage of all this high quality data we had in the past 20 years. We are able to have a good simulation for scenario-based earthquake hazard and the risk assessment. And for that, then we have the simulation, but then we would like to have this low cost sensor to highly populated, installed in many regions in high resolution to have this large scale earthquake ground shaking data collection, and also maybe the open data to everyone, which is able to access the data and understand more. And for the hazard, then we need to understand the risk. So we also, another group of our group working on this open street modules for even using the satellite data to have better capture of the exposure models. And then as I mentioned, we want to put the sensor into the buildings, then we can analyze the building performance. But in the same time, the engineer also would like to use this data for the building health monitoring for any earthquakes impact to the buildings, although it looks okay from outside, but whether from the data we can capture whatever it might impact to this building, especially important for the aftershocks afterwards. And then transparency in the fragility curve, so we are able to understand better risk assessment. Then of course, important part is how to educate the public, how to work with social scientists to have a better interpretation of our results. And we call this Resist as a resilient societies through intelligent smart city technology. This is the project we work together also with Japan and US, and also in kind from New Zealand and Germany and Italy. We try to bring all together to carry on this new idea. The reason we are able to do that is because the advance of the instruments, as shown here, that we develop this QSIS, quake structure integrity sensor under TAG that is very small, like smaller than our hand, and then it's very, low cost, but good performance. And then we are able to have like thousands of sensors in the buildings or with Wi-Fi also, and then we can have the real-time transmission of the data. Compared to the 1960s, as many of you know, it's big, and even at that time, is already expensive. So we can only afford like tens of the instruments nationwide. And now and then in 90s, as I mentioned, the TSMIP program, we are able to install hundreds of stations, but still pricey, consider if we want to put into the buildings for every floor. So this QSIS sensor is the future, and we hope we are able to smoothly develop this to the users. And this is one of the example about the performance of this QSIS sensor. This is the sensor, actually at that time it's QCN, but it's similar inside with one MEMS inside this QSIS. Then in our office here, actually the other building on campus, we install this QCN or QSIS sensor from basement to the top of the buildings. And this is the performance of this sensors in frequency domain. Because for the buildings, we want to see the frequency response. Then you can see from basement to the seventh floor to 11th floor, We see the amplification about 7 times compared to the basement. And also we see the different response in different frequency bands, maybe related to the higher mode of the shaking of the buildings. And this one's actually a very offshore event again, in the subduction zone, and then our buildings around here. So that shows, even though the sensor is very small and very affordable in price, but the quality is really good. So we try to implement all this around Taiwan, and then we try to understand how much we can learn for the impact of the subduction earthquake to Taipei as like this 1920 magnitude 8 events about 100 years ago, and especially for the long period motion for the high-rise building. And this sensor might be able to help us to digest more, to understand the impact of long period motion to the high-rise buildings. But for that, we need to have installation of small buildings arrays from different type of buildings. And that's actually challenging. It's how to convince or persuade people, general public, to have the sensor in their building, and how to access the data, to open the data. That's a lot of complicated issue. And that's the challenging we encounter now is we have the sensor, but whether people feel comfortable to have us to install the sensors into their buildings. And that's another challenge we face. And we would like to talk to social scientists to have the better communication with people. So then we can have a better management from hazard to risk. And that's an important topic for the megacity issue in the theme 3. Well, then I also mentioned here is the Tainan, which is another metropolitan city in southwestern Taiwan with high hazard and also all the high-tech industry. Maybe some of you know in Taiwan, we have all this semiconductor industry. Then that's very important to secure the impact from shaking. And that's also, we would like to develop the early warning or to reduce the impact to all this high-tech industry park. Well, so for that, I just want to show you one example is what we learned from those good data. This is actually the data we collected for the 1999 GG earthquake. Then we developed the 3D simulation. From the 3D for geometry to wave propagation, you can see the rupture from south to north. And then that's why we have high impact in the northern Taiwan and also to Taipei. I would like to play it again is because this is a very good example to show people how earthquake early warning may be possible. Is let me do it again. As I show here, this is the clock, which earthquake was initiated in the first 20 seconds, the rupture on the fault, but to the northern segment of the fault. But we still have time to Taipei. Taipei actually, the wave will impact to Taipei about 30 seconds afterwards. So, well, if we have early warning system at that time, we might be able to save more life. We don't know actually how to really apply this in a practical way, but now we have this early warning to the general public that at least we can have a good infrastructure for using cell phone to inform people the time for the strong shaking. However, when it comes to Taipei, as I mentioned, even though the earthquake is in GG, about hundreds or 200 kilometers away, but we have impact to Taipei. The reason for that is because of the 3D basin structure. This is another example that we have good instruments, then we are able to have a good map for the basin structure, then we can have a better simulation. It shows the wave actually will have all this resonance in the basin and also the shaking for tens of seconds. And people also, during this breakout section, people talk about liquefaction. Liquefaction comes with this high value of peak ground velocity, but also the duration of the shaking. So for the earthquake hazard, we also talk about the chain or multiple hazard after large earthquake. Through the simulation, we are also possible to capture the possible liquefaction region, even for the landslide. And that's all the application afterwards, after the high resolution of the instruments and the structures, we can carry on more to have a better resolution for the hazard estimation. Well, let me go to the next page. Well, so that's somehow give the idea of all these mega cities studies we implement in Taiwan. As I mentioned, that all these subduction zones and the inland one, of course, give the big impact, but most frequent events in liquid subduction zones give the impact to Taipei. And that's how we have to be try to focus more on the understanding of this collision of the liquid subduction zone to Taiwan. That's also come to our project after 2018 Hualien earthquake. The story actually began from, again, 1999 GG earthquake. How many years? 23 years ago or 22 years ago. This one is the one inland Taiwan, and the other one, the Hualien earthquake, is another one ruptured Milong Fault, even though small segments, but also inland. That actually brings us an important opportunity to understand how the fault was moved, or what's the dynamics of the fault zone. How can we learn more from the fault zone behavior through these inland earthquakes? And then at that time, in 1999, we proposed a drilling project, which is important to understand and the fault zone structure, and also to have the in situ borehole seismometers at site. So, story began actually in 2004 for the drilling. I have to say, I am a seismologist. I never do any drilling before, and I even never see a core before this project. But I think this is very important to have a multidiscipline to involve in these projects. That also I learned from geochemists about the mineralogy and petrology, and also for the whole picture of earthquake dynamics. At that time in 2004, for this TCDP, is we mainly would like to understand what's the physics of faulting from large slip. I have to say, before the GG earthquake, we never imagined that it's possible to have a slip up to 12 meters inland. So for this earthquake in the northern portion of the fault, we have a very large slip velocity, like 4 meters per second. That's beyond the number we can image at that time. And also very large dislocation of 12 meters, which is like 4 floors at once in 3 seconds. Then of course now for the Tohoku earthquake, we can have even larger slip, like 50 meters offshore, to bring very large tsunami. So at that time, basically this is the only event inland we are possible to capture the fault zone material to understand how the fault was moved with this large slip in a short time. So for that project, we tried to retrieve the fault gouge for the single slip, single fault. An important thing is also try to understand the earthquake energy budget, how much energy was put into the shaking and also the friction heat. To that also we combine with many other components for biological analysis, gas measurements, the logging and the stress condition before and after the earthquake. Well, only after for this, but we try to understand whether we can capture the stress status before the earthquake. And then after the drilling, we do the temperature measurements, again, try to capture the friction heat. That's another challenging topic in seismology, how much heat was generated or how the fault was moved due to melting and thermal polarization. And then after that, we install a 7-level borehole seismometer right on site to see whether we can capture any fault zone healing behavior. I want to focus on these temperature measurements as this was the first trial at that time, try to really measure the frictional coefficient at site. However, no matter what, the earthquake was in 1999 and our measurement was made in 2002 and 2005. So that would be like 3 years and 6 years after the earthquake. Then we got a very small frictional coefficient down to like 0.06, less than 0.1, which is much smaller than the 0.6, which we usually learn from the Bayes' law. So that gives the challenging or maybe some answer to the question, the fault is strong or weak. It seems like the fault is weak, but the crust is strong. Then how the large earthquake was possible to rupture in such a weak fault. Well, all this, I give a review just this year published as a 20 years anniversary at that time. I tried to put all this information we learned from modeling, drilling, and monitoring into this review article, if you are interested to see what we have done. Well, and come back to the temperature ones, and then that's why for the J-Fast project for the Japan Tohoku drilling, they put the temperature measurements, and also in China, Wenchuan also for the temperature measurements, they all come to very small frictional coefficient, less than 0.1. So that might be the real condition for very small frictional coefficient at site. Well, and what do we learn from the borehole seismometer? And that's also the question earlier, Philippe also asked me about what we can learn or what's the challenging for the future technology of the new instruments. At that time, when I put into this borehole seismometer, because I feel this is the only one we put into the fault, which just ruptured. We know where the fault was. And so we should be able to see something new. So at that time, I try not to do any template monitoring or whatever now people call AI or machine learning, because if I apply machine learning to the data here, then I will not able to discover the new thing, because machine learning have to learn first. That means I have to do something after some people discovered. So at that time, I try to do things in a very basic way, just visualize one by one. I want to see something which might not be able to see before. Then for that, we actually capture one important feature for the event we call it isotropic events, which is the earthquake that we observe very small, like to the magnitude -1 to 1 in scale, that the earthquake only have these isotropic components. M11 equals to M22 equals to M33. In our observation is we only see P wave without S wave. Well, I have to introduce our borehole seismometer. Is we put 7-level borehole seismometer from 950 meters to 1300 meters, and the fault, because as I mentioned, through drilling, we know where the primary slip zone is. That was in 1111. So this is the borehole 4 right on the slip zone. So, and then in this borehole seismometer from borehole seismometer 1 to 7, 7 at the bottom, we see only a P wave without S wave. We see some other converted phases, but mainly dominated by P wave. And this is the particle motion. And we are able to simulate this wave through a very high frequency of 3D simulation. as also I mentioned in the 3D simulation we have in scale from the whole Taiwan, even to this small scale, only like 3 kilometers by 3 kilometers in dimension, that we can go to the very high frequency in the simulation. And the way to capture this event only with P wave is, as I mentioned, the isotropic components. And from that, we can explain the 3 components waveforms in borehole 1 and borehole seismometer 4, for example, as see the strong phase in Z components, smaller in two horizontal components, and also good comparison for the amplitude ratio. And this is also the synthetic for the particle motion. So we suggest that these events maybe is the natural hydraulic events that the GG earthquake in 1999, they actually have a complete stress drop for the Sonopur fault. Then that's why the fault, and also very impermeable of the slip zone, the fluid was kept in the footwall, and this fluid migration give the source for this isotropic event. But this already the story like 10 years ago, so somehow I feel that's already an old story, but still important discovery for the behavior of the fault zone after the earthquake. And the other important observation we also see is we have some event clusters. For this study, we put together for the new discovery and also the template to scan all the records, continuous record for 5 years of data. And we have interesting findings for the event cluster that have the same source duration. For example, the cluster A, for the magnitude from 0.3 to 2.0, they actually share the same source time function. If some of you as seismologists, we know the source time function scaled with magnitude. But for this study, we saw the events actually have the certain nucleation zone that with different magnitude, but still come with the same source time function. And we do the dynamic modeling to understand how this behavior can behave. And again, to the very beginning of my question, to understand how earthquake was nucleated, this maybe give some hint. But this one published in 2016, that's, you can see we actually spent many years to digest what this is, and this mainly published by Dr. Ling in GJI, and also the dynamic modeling in GIL, also again, many years ago. Well, but that's the old story in 2004 TCDP, and I have to say we learned a lot from that, especially try to address the topic on earthquake energy budget, and we think to identify the slip zone is important, and also to capture the friction heat is important for the temperature measurements. But that's also some subjects we didn't really give a good answer yet. And it's kind of ongoing questions whether our new project might be able to answer more of these challenging questions. And that's how we propose this MIDAS project in 2021 right now. That is Milun fault drilling and all-inclusive sensing program. And for the temperature measurements, we try to put the DTS into the borehole. So hopefully we can capture the friction heat for the next earthquake, for the future earthquakes, because it's very active region in Hualien. But a lot of challenges, because we also don't know how fast the temperature was dissipated and how far of the events to our site. So a lot of uncertainty, but I think it's worthwhile to give it a try for this DTS monitoring in our borehole for the MIDAS project. And also learn from 2004 the TCVP. We understand the importance of the fluid and also the fault zone permeability, especially the slip zone is very impermeable, even down to the scale of 10 to the minus 18, 10 to the minus 20. But the damage zone is very permeable. So somehow it's very permeable region, but kept by impermeable layer, and how long the fault zone become permeable, how the fault was healed. That's another important subject, which may be able to be answered from the long-term borehole seismometer we put in 2011, I guess. I kind of somehow lost the track for our borehole seismometer installation. But now actually, thanks to the new technology, as we also addressed early this afternoon for the optical fiber, I think that's very important that we are able to have a continuous observation through our borehole and also to the surface. Then we are able to have a good 3D coverage to our fault zone and also the neighborhood. But in the same time, we still put the classic ones. We still intend to put the borehole seismometer into the borehole. So we are going to have the borehole seismometer and also the DAS. For the optical fiber with DAS monitoring, that can be also a good answer to the question, how can we learn from the classic to the new tools? And we will see how much we can learn from both. Well, the other thing is important thing to understand the fault zone dynamics or original status of the stress. For the GG earthquake, for example, that as I mentioned, we somehow see the complete stress drop of an earthquake that was a thrust, but then all the aftershocks become strike slip. That suggests the sigma 1 stress, the maximum horizontal stress is no longer the maximum, the original one maybe become sigma 3, or in a way release large stress. Then from the logging data from FMI, which is DSI for the dipole sensor, we also see the rotation of the stress near the fault. So that's also important to see how the fault was healed. How can they become ready for the next one? Especially for the Mirun fault. We have very short recurrence interval, which I will show later, is only like 70 years. I think that might be one of the shortest recurrence interval in the world that the fault is that active, and it's inland. So maybe we have the chance to see how the stress was recovered after the earthquake. Well, then I come back to the earthquake itself for some of you to introduce the background of this 2018 Mirun earthquake. The Hualien earthquake actually began with a swarm. It's like tens of swarms making to 5 in offshore Taiwan. Since we have the shaking all the time, we didn't really pay that much attention because we got earthquake all the time. If you are in Taiwan for more than a week, you will experience one for sure. Then unfortunately in 2000, and then 2 days later, there's one rupture right to this inland Mirun fault, as I mentioned, that gives damage. And also for Taiwan, we are able to have the real-time moment tensor inversion compared to very high quality seismic monitoring. Then we capture the earthquake in location, magnitude, and focal mechanism at once by Dr. Xianzong Li from IES. We can capture the earthquake immediately in few seconds, right after the earthquake. And also we have this PLR network, as I also mentioned earlier to Nelly, as this PLR sensor all around Taiwan in time, and we can have the real-time shaking monitoring. But right after the earthquake, we see this high intensity in Hualien, and of course we know the damage, we might encounter the damage, and then all this rescue team can come to this region to reduce the impact or rescue people in any case. Then come back to the earthquake itself. This earthquake is a thrust, western dipping fault point, but the surface rupture is right here at the shallow depths. And this earthquake, even though it's not big, but unfortunately, as I mentioned, ruptured to the inland Hualien and right close to the city. Hualien is not yet the mega city, but still very highly populated. And also is a tourist site because of this collision zone. We have a national park, the Taroko National Park there. And so it's a quite popular scenic area. And this high-rise building next to the fall collapsed. So, and also some damage to the hotels. And that's very important lessons we learned, that we shouldn't build any high-rise building next to the fault. And also some crack and the damage of the bridges. Unfortunately, it doesn't really bring big damages. But come back to the high quality seismometering for the observation. At that time, people always bring the impact of this damage is due to the site effect. But from this high quality of seismic station around Hualien, we have almost every 5 kilometers with one stations. We are able to explain that the damage of those high-rise building is due to this long period motion, or engineering called the pulse-like velocity motion. And we see this, the large velocity near the fault and then decay next to the fault. And so we consider this damage is due to the source rather than from the side effect. And I think that's very important to engineer how to have a better resilience to the impact of this long period motion. And again, there's a publication just actually this year now, and also last year. Well, as I mentioned, this earthquake was active. I mean, the Millen Fault is active because in 1951, we experienced like 5 magnitude 7 earthquake in a month, and especially a couple of them in a week. And this one also ruptured the Millen Fault. This is in 1951, ruptured exactly the same location. That actually suggests the earthquake can repeat and actually give the similar phenomena too, even though Hualien earthquake in 2018 is smaller in scale. But this is the damage in 1951. Fortunately, in 2018, all this, we don't have this large damage wise. But interesting thing to show is this is the factual in elementary school, and the same fractal zone appeared in 2018. And also all this population, I mean, the damage region is almost identical to the literature reported in 1951. And that gives, again, important message, and also to understand how the fault was moved. Another important thing or interesting feature for the Hualien earthquake is the main shock was western dipping thrust. But at that time, we are so puzzled because the Millen Fault was considered as a strike slip fault. So Millen Fault is oblique strike slip fault, but the main shock is a dipping west thrust. However, for the aftershocks, using these portable stations to analyze all these aftershocks focal mechanisms, it shows they are all normal fault. So one earthquake sequence, we have all the stress condition. We have the thrust, we have stress slip, we have the normal fault. That suggests the complication of the stress regime near the subduction zone and the Millen Fault. And we also try to understand why with Millen Fault it's so easy to get triggered for the events nearby. And in the same time, from the INSAR and GPS and ALOS, it also showed the rotation of this block of the Millen Fault. That gives some hint of a seismotectonics in this region. And we can have some monitoring for the GPS, the motion horizontally and vertically from INSAR and GPS. And also the subject we addressed also early this afternoon. And using all those data from GPS, INSAR, and storm motion, we are able to give this slip distribution for the spatial and slip distribution. And for that one, they go from offshore and then go to the inland and then come to another segments. So even though the magnitude is 6.3, but rupture 3 segments at once. That suggests how complicated it is for the setting here, with several geologists that give the model the subduction zones to the Midland Fault, with this Luzon arc, with the Central Range Fault, and so on. So for the MIDAS projects, from Yan et al., it also suggests this Midland Fault might have a good link to all the nearby structure, which give the important channel network if we want to capture some earthquake precursor as whatever the subjects people are also very keen to have. And this observatory site maybe is also possible to capture the precursors for the future big ones. And again, this is the earthquake in this region. Actually, after 2018, we have all the sequences. In 2019, 2021 is all somehow our neighbor, this 2018 region. But important things, nothing at the shallow depths. But whether the shallow depths was locked or somehow when this shallow portion may be ruptured, and how can we capture that for the better forecasting of ground motions? That's always the challenging to do. Well, sorry to take out some time. I want to come to this MIDAS project. For the 2004, we learned earlier, 10 years ago, and to 2021, we tried to install or implement this high-tech or this forefront science for the optical fiber, the GPS, the strand meter, and so on. Also to map the seismogenic system from subduction zone offshore to inland fault structure. So then we are able to have a good simulation for the ground motion and even to the buildings in another projects. And then also the sample, the slip zone, which is frequent rupture. And also people always question about the precursors. Are we possible to capture some precursors? We don't know, but maybe it was well to try. And this is the site we put in for the Midland Fault near the Chisintan. Seismic profile suggests we want to put 2 boreholes on the eastern side, in southeastern side and northwestern side, 2 boreholes, and then cover this with optical fiber to have a 3D mapping of the fault structure. So actually, we are now actually ongoing. Yesterday, we have our first core, but for the cutting, we actually see some possible fault zone feature. We put, as I say, the borehole seismometer, the optical fiber here, and then going from A cover to B, and then we would like to have another hole C for hydrological observation for geochemistry and gas and fluid. And we are actually in a pretty good stage.
I'm sorry. I think we need just to conclude because we reach the maximum time. Thank you so much.
Right. Sorry for that. Well, then that's the fiber one. We expect to have that one, and then get ready actually for the sensor. Actually, I close to the conclusion already is that we want to have a good observatory to implement the DAS, and thanks to Philippe actually for the arrival of the DAS sensor, and hopefully we are going to install this within a month, and we'll be happy to share the results and the data, and then we hope to have a good observatory for all these observations, and then to bring into the buildings and so on. So then we can have a better capture of all the data to have a better evaluation of the hazard for our mega city for resilient society. Thank you. Sorry for the time. And I hope that I give somehow the presentation to what we would like to deliver in the near future. Thank you very much.
Thank you. Thanks a lot, Kuo-Fong, for this very nice talk, which is showing the progress of thoughts actually from how to start from a phenomena which is a quake to the hazard, knowing where the faults are, and the recurrence of earthquakes, and then to the risk, because these earthquakes and faults are close to the megacities at risk. So the techniques were very broad scope and cover. You asked for that to cover largely the issue discussed today. Indeed, it was a bit long, but that was very interesting. I think everyone appreciated it, and I don't know whether we have time for questions. Maybe David or others can tell us if we can get 1 or 2 questions, even if we are after the time. Is there an urgent question to be? No, probably not. So I have just one. You mentioned machine learning may not help for new discovery of science. I kind of agree with you, but certainly for monitoring and real-time information analysis and processing for early warning systems, this may be very important. Can you comment on this very shortly?
Yeah, actually, I have another project using AI for early warning. Well, it's just the new stage. I was looking forward to the advance of the machine learning from the data, especially for the fiber. We have big data coming, so it's difficult to measure that in a human way. So what I was saying is, for very somehow delicate discovery, machine learning might be able to capture some, but still we need the human learning first. And that's actually the point I always want to address. Yeah, we have to learn from ourselves and then also to learn from the machine. We'll see for the new era.
Sure. Thank you very much, Kuo-Fong, again, for this very interesting talk. We have now just half a second to mention that there are themes 5 to 7 tomorrow, and maybe Paolo wanted to say something about this.
Yes,
Thank you again, Kuo-Fong.
I just highlight to all the people are following us that tomorrow we have team 5, 6, and 7 that we are very, very interesting. Is the 3rd day, so we will start at 7 GMT and 3 p.m. in East Asia. Team 5 is related to natural hazard forecasting. Team 6 is related to multi-hazard relationship. And Team 7 is about natural hazard communication. So again, like this morning, we will start at 7 GMT and 3 p.m. in East Asia. See you tomorrow for the last day.
Thank you. Bye-bye.
Thank you. Bye-bye. Talk to you soon, Kuo-Fong.
Thanks, Philippe. I'll talk to you more when you arrive. Maybe tomorrow. Okay.
Let's see.
Yeah.
Bye.
Actually, it's a holiday today, so that's why. Maybe tomorrow.
Ah, that's why. Okay.
Yeah. Okay.
Bye. Bye. Thank you. Thank you.
Bye-bye.
Bye.
Bye. Thank you. Thanks a lot for hard work. Nice to work together. That's good. That's bye.